I'd like to begin with this thought experiment. I'm sure a number of you would be familiar with the Drake equation. It's a way of trying to get one to think about how the prevalence or possibility of the prevalence of extraterrestrial intelligence in our own Milky Way galaxy. And so the idea is that you have all these terms that are multiplied together. You start with the rate of star formation in the galaxy, the fraction of these stars which have planets, the average number of these planets that may develop an ecosystem. So that's sort of broadly taken to mean those that are in the habitable zone. Then there's the fraction of these that are in the habitable zone that actually develop life, the fraction that develop intelligent life, the fraction of intelligent life that's actually communicative. And then L is the length of time for which they're communicating. So this is quite a significant term. So of these terms, it's kind of quite difficult to tell, especially the latter four, what they are. But in recent years, missions like the Kepler mission have discovered that exoplanets are extremely prevalent. So the fraction of stars which play host to exoplanets is very close to 1. We can say that with quite a lot of confidence now. And we've also got some answers to these other terms, like the rate of star formation between 1.5 and 3 stars per year in our galaxy, and the fraction of planets which are in the habitable zone, which is around about 1 in 5. So these are fairly large numbers, and that's led a lot of people to be very interested in the possibility for the existence of life. In particular, the discovery of that most stars have planets. So I'll just briefly introduce Breakthrough Listen. So I'm a postdoctoral scholar with Breakthrough Listen at the University of California, Berkeley. And Breakthrough Listen is a large effort to search for technosignatures, to search for evidence of extraterrestrial intelligence. And there are a number of facets to this project, but the main ones are things like more than 1 million stars and other objects, open source data, hardware, instrumentation, and software. I put some links there, and to basically become the most comprehensive search for evidence of extraterrestrial intelligence ever conducted. So maybe I'll begin with what these technosignatures actually look like. So this is actually unknowable. We don't know what a technosignature could look like, but it makes sense to start somewhere. And one such area to look at is our own emissions. For example, here is the Voyager spacecraft, and I'll speak more about this later, and you'll get a chance to play around with some data. This is the most distant human-made object ever from Earth. It's been in operation for about 45 years, I think, maybe 46 soon. And it is a very good example of what we might consider a technosignature to look like. So you can see on the bottom right is a waterfall plot of transmission from the Voyager probe. And there are a number of kind of characteristics of these signals that lead us to know that it's a technosignature, but I'll speak about 2 of the main ones. For example, one is that it's a narrowband signal. You can see the kind of very powerful narrowband feature in the waterfall plot there, and this is something that can't be generated by any known astrophysical process. So that's an indication that it's of technological origin. And another interesting example that you can see in this plot here is that they have a drift rate. So you can see that they're drifting in frequency, and this implies a relative difference in acceleration between the observer and the transmitter, which also is an indication that it might be of technological origin in this case. But more on this later. This is a very difficult task. Essentially, what we're trying to do is distinguish between astrophysical phenomena, radio frequency interference, and everything else, which is technosignatures. And you can see there have been various objects and sources in these different parts of the Venn diagram before. Pulsars were very briefly considered to be one of all 3. Maybe they were all considered as possibilities. FRBs for a while were confused with these peritons, which were later determined to be RFI. and that was in doubt for a while, but ultimately it was determined that they were indeed real and very interesting. And BLC1, this was a signal that we investigated that was very interesting. It passed a lot of our checks, but ultimately was discovered to be RFI. If you'd like to read more about some of the details of this technosignature detective work that went into that particular signal, but could be applied to other signals, please take a look at that paper. It's very interesting. They go into a lot of detail about all the little checks that you can do once it's passed the main checks. So single dish SETI is how Breakthrough Listen started, and a lot of SETI searches were conducted by single dish telescopes. So large single dishes like the Green Bank telescope in the United States and Marianne or Parkes in Australia. And the way one of the ways that we conduct SETI with single dish instruments is to look at the star of interest where you're hoping to see a technosignature, where you're looking for technosignatures. And then you move the telescope away and look at another source, and then move it back and look at a different source and then move it back. And what you should see is that if it's a real technosignature that's localized to that star, you should see that the signal appears in the on observations, but not in the off observations. Because if it appears in the off observation, that implies that it's RFI from nearby. So if you take a look at the plots on the right, this is some real data that we took. But this is more of an example here. So if we looked at A is the source that we're looking at, and then we move the telescope to a source B, or move it to C or D, we see that we only see the signal in the A observation. So that lends evidence to suggest that that signal really is coming from the source A. So that's something that we would look for with a single dish telescope. Some of the other things you can do is have like a dual receivers. So you can have you can do it simultaneously. You can have one receiver looking slightly offset to the main primary receiver, and you don't have to do, you can get A and B simultaneously, which is a lot better for RFI rejection, because you would see the exact same signal in both if it was RFI. So this is broadly how we've done single dish SETI so far. But SETI with array radio telescopes offers some significant advantages. So with MeerKAT, you get a very large field of view, but you also get a lot of collecting area because you have many small dishes. You can synthesize coherent beams on sources of interest in the primary field of view. I'll explain that a little bit more. And there are excellent options for RFI rejection that you don't really get as easily with single dish telescopes. And particularly in the case of telescopes like MeerKAT, there are a lot of opportunities for commensal observing just by virtue of the way the telescope has been architected. And I'll explain a little bit more in coming slides as well. So just a rough comparison of the collecting area. One GBT dish, which is 100 meters in diameter, is equivalent to maybe 55 MeerKAT dishes in collecting area. So you can see how these things compare. But on the other hand, Green Bank telescope has a very small primary field of view compared with MeerKAT because of dish size. So the advantages of having a large primary field of view is that you can form synthesized beams, coherent synthesized beams on objects of interest within the primary field of view. So in this kind of diagram here, you can see MeerKAT on the bottom, and this is the primary beam. The red object in the middle is maybe what the primary observer is looking at. But commensal observers can form synthesized beams anywhere in that green instantaneous field of view, which is quite large for MeerKAT. So just one other thing to mention is this is not to scale. The synthesized beams are much smaller relative to the primary field of view. So they're only 15 arc seconds. Whereas I think at L-band, MeerKAT is around about a degree or so, depending on where you are in L-band. Right, so how would we conduct SETI with an array radio telescope? We definitely don't need to do on-off pointings like I showed for single dish telescopes. So to illustrate this, imagine that we see a signal in one of the commensal beams that we formed here, one of these blue beams. And if we were to look at all the other beams and we saw that there was no signal matching signal in any of those other beams, then that gives evidence that the signal might be real from that particular source. However, if we see that signal in the other beams, then that's evidence that it's a nearby source of RFI, because you shouldn't see it in other sources. So this is really one of the main approaches that breakthrough listen is doing at MeerKAT, commensal SETI and commensal beamforming. We're forming both coherent and incoherent beams. And the aim is to observe more than 1 million nearby sources, which is underway as we speak. This is kind of how our system fits in at MeerKAT. So MeerKAT is built around kind of Ethernet interconnect fabric, 40 gigabits Ethernet, and multiple different users can subscribe to data simultaneously. You can see the other USEs, or user supplied equipment systems, and we are one of those. And we receive data from the F engines. And I'll show, oh, that's coming up. So this is basically the approach we're taking with our current automated commensal SETI system that's running at the moment. We receive packets, receive coarse channels from the F engines. We write this data into NVMe modules. We fetch calibration solutions and targets within the current field of view, and upchannelize and beamform on these targets, run our SETI search algorithms, coming to that as well, store the SETI search products and raw voltage snippets. That's another thing I'm coming to as well, and then rinse and repeat. So one of the reasons we don't store all the data is because the data rate out of MeerKAT is just so large. So at Greenbank and Parks, we would store everything we record in large storage nodes on site. MeerKAT, we also have storage nodes, but because of the size and of the incoming data, we are instead, when we detect an interesting signal, we are excising that signal in the raw data and saving the raw data still, but just around the signal of interest. So it's a slightly different system, but it allows us to store some raw data from the signals we detect. This is a diagram of the full system. Basically what I mentioned before, but we ingest the packets, upchannelize, beamform, conduct a SETI search, and then extract these raw voltage snippets and write them to disk. And then on the bottom, you can see all the kind of metadata services that run to automate the entire system. So this has to run automatically alongside every primary observer without intervention. And yeah, so you feel free to ask me more questions about this, but I don't want to go into too much detail now. Okay, this is an example of the output of our techno-signature search. So we have a system that does a narrowband Doppler drift search. We look for narrowband drifting signals. And once a narrowband drifting signal has been found, then we go back and extract all the raw voltage snippets. So this was one signal that was detected in a coherent beam. And the system has gone back and extracted the raw voltage data from each antenna at that exact time. So you can see, I'm not sure how clearly you can see it, but there is a narrowband drifting signal in each of these antennas. So you can see how we extracted that raw voltage region. And then later on, we can reconstruct all the processing steps that we did to make the detection. So it will help us determine whether we made a good detection or not in future. Okay, briefly, our hardware, we have quite a lot of processing nodes and storage nodes on site. And there's another installation trip in a few weeks where we're going to install the remaining 16 machines. That's one half of our system on the right there in the KDRA. Okay, I have a few slides on source selection. So what are we actually going to observe while we're doing our SETI search? Our main sample is this 33 million star all-sky sample derived from Gaia data. And you can see some details. 95% are within 2 kiloparsecs, so they're all very close. And close to 20,000 are in the Earth transit zone. So these are stars which would be able to detect Earth as a transiting exoplanet where they're doing these observations. So you can imagine how that might look on the sky. And then we have other catalogs that we're looking at. The Breakthrough Listen Exotica catalog put together by Brian Lackey is very interesting. It looks at all kinds of unusual exotic astrophysical objects. And there are 4 main categories, and it's quite interesting. And I recommend reading that paper. It's fun. Okay. if you're interested in actually playing around with this data and looking at the targets, you can download the targets list, the entire database, as a CSV file if you want. And there's an associated paper which explains how it was developed and how to use it and so on. As part of our systems at MeerKAT, we also have a target selector process that, based on the kind of instantaneous primary field of view, it determines what object to look at, what objects are available, and then ranks them by priority and publishes a message downstream processes that new targets are available, and then the beamformer goes and beamforms and conducts the rest of the SETI search. And this is a projection of observing progress. So this is sort of quite a conservative estimate. If we have two banks of processing nodes, one processing, one observing or recording, and if that processing time is approximately 15 minutes or 45 minutes, it's actually much closer to 15 minutes or 10 minutes as it's in practice, which is what we have running at the moment. So that dotted blue line is sort of a bit obsolete. It's more like the solid line. And you can see we get to about 500,000 stars in 180 days, which is really fantastic progress compared with how rapidly we've been able to observe with single digit telescopes, which have to move from source to source. And, yeah. So this is entirely commensal, and this is projected. So we'll have data. Our searches are sort of ramping up as we speak. Right. Okay. I've included some links here to our software. Feel free. It's all open source and available. All our breakthrough distance data will be publicly hosted, and we add to this publicly hosted data. Well, all these data sets we add to them all the time. So I think there's about two petabytes up at the moment. And I wanted to mention our collaborations with other radio telescopes. So here's the Allen Telescope Array in California and the Very Large Array in New Mexico in the US. And similar sort of commensal, and in the case of the 88 primary SETI search systems have been built, and there's some sharing of software and expertise in these different areas. And let's see. So up next, we will be taking a look at how to actually detect a technosignature, starting with Voyager. So you'll have an opportunity to play with this data yourself. It is actually an extraterrestrial technosignature, and yeah, the subject of our first practical sessions. But before we get to that, just a note on our contributors, and yeah, thank you very much.